Welcome to this video introducing Chemistry 2 Spectroscopy course. Students should watch this video in advance of beginning the course as it provides an overview of the background knowledge for the course. So why do we have a video introducing the course? Spectroscopy is about the interaction of light and matter and how we use an understanding of those interactions to study molecular orbitals. This is quite a broad topic and so relies a lot on previous knowledge. As we won't have time to go over this previous knowledge, I'm highlighting it here so that students have a chance to review any material they are unsure of in advance of our course. Once we've finished Chemistry 2 Spectroscopy, you'll be ready to take on Chemistry 3 Spectroscopy next year. This course will build on what we cover in Chemistry 2 and move the discussion on to more complex systems by removing some of the assumptions we make or looking at more complex molecules, as well as more advanced processing of spectroscopic outputs, really squeezing the data that is generated for lots of molecular level information. That's what makes spectroscopy so powerful and interesting. So in summary, the aim of your time watching this video is to remind you of the key learning outcomes from the previous courses and to point you to resources if you want to refresh this learning. It's not intended to reteach all of that material. That would be impossible in this short video. One key note, our course is self-contained, but obviously if we are relying on previous knowledge, it is important for an understanding that you are aware of those concepts covered in previous courses. So these are the topics we are going to go over briefly. As I do so, I will point out why we are particularly interested in them for the purpose of spectroscopy. Let's start. The first key underpinning topic is electromagnetic radiation. Obviously, if spectroscopy is a study of the interaction of light, that is electromagnetic radiation, and matter, then we need to know what we mean by electromagnetic radiation. Electromagnetic radiation can be described as a wave or a stream of photons. Considering it as a wave, we can see that it can be defined as having a wavelength, lambda, given the Greek symbol for the letter L, and if it travels at a speed c, then we can determine the frequency of the wave by measuring how often the crest passes a particular point. Frequency is given the symbol nu, the Greek letter for n. Frequency and wavelength are clearly related by the speed at which light travels, and we can describe the relationship by this equation, where c is the speed of light in a vacuum. Note the units of wavelength and frequency, and note that the symbols for frequency and the letter V look very similar. We will use V for something else though in this course. The electromagnetic spectrum is shown in the figure. You can see that the electromagnetic spectrum runs in both directions. We have at one extreme electromagnetic radiation of very short wavelength, gamma and X-rays. This is high energy radiation. At the other extreme is very low energy radiation, microwaves and radio waves, with very long wavelengths stretching into the meters. In the middle we have the UV visible region. This visible region is so called because its energy triggers responses in our eyes, and so we can register and hence distinguish between those energies, which run along the colour of the rainbow from low energy, red, to high energy, violet. At just slightly higher energy again, we have the ultraviolet region. We can't distinguish this by eye, and its energy is such that it can cause damage to human flesh. To review electromagnetic radiation, have a look back at your Year 1 spectroscopy notes from Chemistry 1A. We mentioned that light can be considered as waves or a stream of photons. This wave-particle duality came about because classical view of light as a wave did not explain some experimental observations. You'll have seen some of this in quantum theory, such as blackbody radiation. Quantum theory allows us to consider a ray of light as a stream of photons and was described by Max Planck in 1900. This means that the energy of light can be related to its frequency and the intensity related to the number of photons present at any particular time, according to the general expression shown. The constant here, h, is Planck's constant. Note the value and units carefully. We add in the variable n into this equation here just to emphasize that energy is quantized. In other words, it increases in unit amounts depending on the value n. Evidence from this came from the photoelectric effect and later the Compton effect described in your quantum theory lectures. The photoelectric effect showed that a certain energy threshold of light incident on a metal must be met before electrons were ejected from a metal. This is, of course, of fundamental importance in spectroscopy. It is telling us that for particular types of spectroscopic transitions, a minimum energy or a threshold frequency is necessary. We will relate this to the idea of spectroscopic transitions. We saw the electromagnetic spectrum before in terms of wavelengths, but we can show it again now in terms of the types of interaction that can occur in matter upon interaction with light of different frequencies. This gives rise to a range of spectroscopies, each with their own instrumentation, with light sources and detectors matching the energy of interest. In Chemistry 2 course, we will look at 3 of these spectroscopies in particular: rotational, vibrational, and UV-vis spectroscopy. So this slide summarizes the key things you should know about electromagnetic radiation and quantization from previous learning. If you're unsure about any of it, be sure to review it in advance of our course. Let's move on to briefly look at some of the other remaining topics. Obviously, from school and Year 1 learning, you will be very familiar with the concept of atomic spectra. When we provide a high energy burst to atoms, e.g. in fireworks or sparks of light, we observe emission from those atoms, but only at very defined energies, called line spectra. The fact that these energies are defined means that only certain energy differences are observed. This introduces us to the idea of transitions. Electrons move from one level of defined energy to another. Transitions are the basis of spectroscopy. We see here a range of possible transitions in the hydrogen atom. These are emissions, electrons moving from a higher energy level to a lower one. The actual spectrum would show defined lines where there is distinguishable energy differences, but as we go to higher n values, it becomes harder to distinguish, and we get what's called a continuum. To review this further, check back on Year 1 spectroscopy. Before quantum theory, this could be related to the Bohr model of the atom, with these energy differences being considered to be transitions between shells. We could even calculate the energy difference using the Rydberg equation, and while we have moved away from the Bohr model, the key message for us here is that the energies of spectroscopic transitions clearly relate directly to the difference between the energy levels in the molecule, however those energy levels are described. Most of the focus on line spectra is on emission spectroscopy, but the opposite is also true. We can see that atomic absorption spectra, where atoms absorb energy corresponding to differences in energy levels, are also characteristic of an atom. This gives rise to a very powerful analytical chemistry technique called atomic absorption spectroscopy, AAS. So this slide summarizes the key things you should know about atomic spectra from previous learning. If you're unsure about any of it, be sure to review it in advance of our course. Let's look briefly now at wave functions. We mentioned that electromagnetic radiation can be considered as a wave or a bundle of particles, and this wave-particle duality is true for all matter, including electrons. We can see this is true from the diffraction pattern generated from electrons. We have constructive and destructive interference, meaning the electrons have wave characteristics. The Schrödinger equation introduces mathematical descriptions of these waves, and its solutions for the hydrogen atom, described in much more detail in the quantum theory course, again shows us that energy is quantized, depending on the number n. Note the similarity of this equation to the Rydberg equation derived from the Bohr model. For us in spectroscopy, this re-emphasizes the quantized nature of energy and allows us to describe the behavior of electrons involved in transitions. Nearly there. Since you've already covered atomic spectroscopy, in Chemistry 2 we are going to move the conversation up a bit to molecular spectroscopy. Diatomic molecules are the easiest next step, so they will be the focus of this course. As you'll see, we can take a lot of what we learn here and apply it to more complex molecules. You know that a diatomic will have certain bond length, depending on the size of the orbitals involved in bonding. Bond lengths in the figure shown run from about 74 picometers to nearly 4 times that value, 266 picometers. There is also a bond strength. How difficult is it to break this bond, shown in the table and described as dissociation energy? We'll be focusing on the interaction between light and these molecules in spectroscopy. For the molecules shown in the table, there will be an equilibrium bond length, a point at which the conflict between the attraction between one nucleus and the electrons on the other atom, and the repulsion between the electron clouds around each other are at the lowest energy. Obviously, if we pushed these atoms together so that they were closer, the energy would increase due to interatomic repulsion. If we pulled them apart, we would have to first overcome the attractive forces between the atoms that break the bond, but then reach a stage where the atoms are so far apart they don't interact. The bond is broken. At this stage, the energy does not depend on the distance and it flatlines. We see here the depth of the well created is the bond dissociation energy, and the whole system is described by the bond length. This potential energy well describes the electronic interactions in a molecule, and therefore it's a good description for any electronic level. Because of the way light interacts with molecules is dependent on their energy, we can easily gain structural information. You've described molecular orbitals previously in your MO theory courses. The main message here is that each of these molecular orbitals has its own potential energy curve, and we can see that the transitions can occur from a range of occupied levels to a number of unoccupied orbitals. These are the basis of electronic transitions that we will be exploring. Finally, spectroscopy is a topic that is full of weird and wonderful symbols and units. You'll need to take care what units you are using and make sure you note them at all times. A number without a unit is meaningless. We've covered some of the common ones before. You'll be familiar with wave numbers from infrared spectra you may have seen in the past. Wave numbers, or centimeters to the -1, are a common way to describe energy in spectroscopy, and I've shown here how we relate wave numbers to joules. A good trick is when you see a bar over a variable, it emphasizes that we are using units wave numbers. I'm looking forward to starting this course with you. We'll be covering these 3 topics in detail, showing the power of spectroscopy in finding out a lot about molecular structure and properties. And I'll see you soon.